let's discuss classification. Now, classification is the other branch of supervised machine learning. And in classification, what we're trying to do is we're trying to predict categorical labels. In regression, we try to predict quantitative numerical labels. And because of that difference, because of those two differences, we cannot use the same metrics that we would use for regression. So in these sets of lectures, let's talk about the metrics we would use for classification and let's discuss a common classification algorithm. An example of classification is, can you classify an image? Given an image, is it a dog or is it a cat? In that example there, we have a binary classification problem. We only have two classes. Now, we're not restricted to binary classification. In fact, we can have more than two classes. If that's the case, it's called multi-class classification. Now, with regression, remember we're trying to construct a function. We're trying to find a function f to take a set of observations and predict continuous values. Very similar with classification, we're still trying to find this function f given a data set x to make classifications. So the y values that are going to come out of our model are going to be discrete values. They're no longer going to be continuous values, they're going to be discrete values representing the classes that we can have for our problem. If we go back to the binary image classification, we can assign one label. Let's say cat, we'll assign it a label of 1, and dog will assign it a label of 0. So our model will only return 0 or 1, and those will be mapped to the classes that we have. If we're working with more than two classes, then our y values can be just more than two values. If we're trying to, let's say we have three classes, let's say we're trying to classify what species a flower belongs to, a specific iris belongs to. Let's say we have three classes, then the model will produce 0, 1, or 2, and then we can map those numerical values to a particular class. As I discussed, it doesn't make sense to use the metrics for regression to evaluate a model, a classification model. With regression, we predict continuous values. We would do things like mean squared error, mean absolute error. Well, in this situation, it doesn't make sense. We don't have continuous values. We don't have continuous labels. We have discrete categorical labels. So what would be a good metric to use for classification? Well, one metric we can use for classification is accuracy. Essentially what we're trying to do, what our model is doing, is it's telling us whether this observation, what class this observation is in. So we either got it correct or we got it wrong. It's binary. So because of that binary nature, we can use accuracy. We can measure how accurate our classifier performs, how much accuracy it has. So, for example, if we tested out with 100 images, and out of those 100 images, it got 77 correct, it correctly classified 77 of those images, then our accuracy is 77%, 0.77 for use fraction. So we can define our accuracy as the number of correct observations over the number of observations. Now, is accuracy always a good metric to use to evaluate our model? Let's think about it. Is it a good metric to use all the time? What might be some problems with using accuracy? Well, let's consider an example where we're trying to train a model to detect disease. And only 10% of our observations have the disease. Then a naive model, a naive classifier, will always predict the majority class, will always predict that people do not have the disease. So given the fact that only 10% of the population have the disease, what would be the accuracy of this naive model that always predicts the majority class, always predicts that people don't have the disease? Because that's the majority class in this situation. that means that our model will have a 90% accuracy. This very naive model that doesn't really do anything, just always predicts people don't have disease, will be 90% accurate. And that's a problem, because if I tell you I have a classification model and it's 90% accurate, if I don't tell you anything else, it might seem that I have a very good model. Oh, 90%, that's pretty good. Well, we got to consider what is the balance between our two classes in this case. So if we look at it, it says, wait a minute, only 10% of the population has the disease. So a naive model will always predict the majority class. Then your model you're telling me has 90% accurate isn't so impressive. So maybe there's other metrics we can use instead of accuracy that won't have this problem. And two metrics we can use that won't have this problem is the idea of precision and recall. In disease detection, we are more interested in determining our model's performance with regards to a class representing the disease. In other words, we're more concerned about we're more concerned about how well our model perform at really identifying that someone has disease. So we're going to call that our positive class. We're going to call having disease positive. And we're going to call not having disease negative. So one thing we could go ahead and do is we can construct this table here called the confusion matrix. On one axis, we have the true label of the observations. Is it a positive observation? In this case, does this person indeed have the disease? Or is it a negative observation that the true value is this person does not have the disease? And the other axis we have, what is our prediction from our model? Did our model predict the person has disease, or did our model predict the person did not have the disease? So given the fact that we have that a model predicts two values and we have two classes, then we have four different types of outcomes. We can have a situation where someone has a disease and our model says, oh, in fact, the person does have the disease. We're going to call it a true positive because our model says the person was positive and that was correct. That was true. So it's a true positive. Then what if the person doesn't have the disease, but we say they do have the disease? That's incorrect. So that's a false positive. So that positive label we assigned, that positive label the model returned is false. So it's a false positive. Now let's look at the situation where someone does have the disease, so they're positive, but our model was incorrect and said they did not have the disease. So that negative label we assigned to them, that was false. That's not true. So we call that a false negative. And the last situation that can happen is if an observation is negative, so they don't have the disease, and we correctly say they don't have the disease, well, since that's correct, we're going to call that a true negative. So it's four different outcomes we can have here. Now let's define two metrics. Let's define precision and recall. So precision is the number of true positives over all positive predictions, while recall is the number of true positives over all positive observations. So these are the equations we have here for these two metrics. So let's talk about what these metrics represent. So if we have a model that has a high precision, then what is happening is that we are being very conservative, very stingy in assigning positive labels such that we can reduce the number of false positives. A high recall, if we have a model that has a high recall metric, that means we are prioritizing catching all positive observations by reducing the number of false negatives. So precision is going to be a measure of how precise our model was. In other words, when it said someone had the disease, how precise was it? How precise was it in saying this person has disease? That's precision. Recall is a measure of, well, of all the people who have the disease, how many were you able to properly identify? How many of those were you able to catch, to recall? That's what recall is a measure of. So now let's go ahead and talk about that naive model. That model that always predicts a person does not have the disease. Given that this model always predicts this person does not have the disease, what is the measure of recall? What is the recall of this model? If we say that someone has a disease as a positive label, what is the value of recall? We understand it's going to have 90% accuracy. That's a misleading. So let's go ahead and calculate things like recall and precision for this naive model. So we see in the numerator of recall, it's true positives. If our model always predicts the person does not have the disease, then there are no true positives. They didn't properly identify that someone had the disease. So in the numerator, we have 0. And we have a lot of false negatives, right? We have a lot of times we're saying someone doesn't have the disease, but in fact, they do. So because of that, this naive model will have 0 recall. It was not able to identify any of the positive observations. So our accuracy might be 90%, but our recall suffers. It's at 0. So the question I pose to you is, of these two metrics, which one do you think is more important? Which one should you emphasize more? Which one do you think is more important? I think it's more important to have higher precision or higher recall. What are your thoughts? Well, in disease detection, you can argue it's more important that we have high recall. It's more important that we identify as many people as possible who indeed have the disease. And perhaps in our effort to have a high recall, we're going to sacrifice precision. We're going to sacrifice, or what's going to happen is that there's going to be situations in which we tell someone has a disease, but they don't have a disease. What do you call that situation where a model says you have the disease, but that person does not have the disease? What is that called? Given this confusion matrix, this table we have above, what is that called? That's called a false positive. It's false that this person is positive for the disease. So if we look at the equation for precision and recall, false positives do not factor in anywhere in the equation for recall. It does, however, factor into the equation of precision. So in our effort to have a high recall, we're going to make mistakes with regards to assigning positive labels. We're not going to be as precise. And we see that it suffers because that false positive number is going to be larger, it's going to increase, and we're dividing a number by, that part belongs in the denominator, so this metric gets reduced. However, what if I tell you that in this situation, if we do say that someone has a disease, then the second round of tests, we have to do some second round of tests, and those are rather invasive and rather risky. And let's say the disease we're working with is slowly progressing and occurs in a lot of elderly people, and to be frank, that this disease, by the time it becomes a major concern, the person probably has died from some other ailment. In that situation, then maybe it's not so good to have a model that is going to have a high recall, identify all those people who have the disease, because those second round of tests are going to be rather invasive and put their health at risk. So given that, perhaps it's better to have a higher precision. So what I'm trying to cast here is that I'm not saying that precision, I'm not trying to give you a definite answer of which metric is more important, precision and recall. What I want you guys to start thinking about is that there is some trade-off between a model's precision and a model's recall. Yes, you want the model to have a high precision, high recall, but there is a trade-off. In other words, if we try to achieve a higher precision, we're going to sacrifice recall and vice versa. So for model evaluation, when trying to identify which model is better, we look at the precision recall score, we need to consider which one is more important for our application, which one is more important for the task at hand. And you have to decide that. You have to decide which one makes sense. So you need to consider in which is a better metric to use to evaluate a model. The thing you need to consider is consider the cost of false positives and false negatives. If you have a large number of false positives, that's going to reduce your precision. If you have a lot of false negatives, that's going to reduce your recall. So which one is worse? In your situation, which one is it worse to have? Is it worse to have a high false positive rate or a high false negative rate? And when I say you got to consider the cost, I don't necessarily mean cost as financial cost. It can mean environmental cost. It can be societal costs. It can be whatever you define cost. You need to sit down and decide which one is better. What do I want to reduce? What is worse to have? False positives or false negatives? You have to come to the conclusion such that you can better evaluate which metrics should you use to compare different models. Let's consider the example for admissions to a top-tier university. Do you think this is going to be a high recall or high precision process? Well, for admissions, there's only a finite number of slots. There's only a finite number of slots. We can't admit everyone who is qualified for this university that reaches some threshold of qualification. So because of that, we got to be very, very precise in when we make our selection process. In other words, we want to make sure that since we cannot admit everyone who is qualified, we want to make sure that when we admit someone into our university, we are very certain that they are qualified. So we want that high precision. We want that precision in this model. So because of that, admissions at top-tier university you can view as a high precision process. Less concerned about trying to identify everyone who meets this criteria to go to our university. Instead, since we have those finite number of slots, we got to be very precise. We want to make sure when we do admit them, we're very certain that they're going to succeed at our university. Now, those metrics we talked about, precision, recall, and accuracy, we can calculate those using scikit-learn. We don't have to do it on our own. We don't have to program a function to calculate things like accuracy, precision, and recall, which we should be comfortable enough to do so. But why reinvent the wheel? So we're going to import the metrics module, and within here, there is the precision score, recall score for these metrics. So it'll tell us the precision and recall. So let's go ahead and do that. Let's generate some data. And there's also the classification report function. We'll show you what that looks like. So notice here we have a precision of 2/3 and a recall of 0.8. And in this classification report, what it does is sort of like a nice summary of what went on. One of the things that you should have noticed, or I'll point out here, is that these equations, precision and recall, it matters what we identify as a positive label and what we identify as the negative label. In the example I talked about with regards to disease detection, we said having disease is positive and not having it is negative. But we could go ahead and flip those around. Those are arbitrary. Those positive and negative, those are arbitrary how we assign what is positive and what is negative. And because they are arbitrary, depending on what we assign as positive or negative, we're going to get different values for precision and recall. So what this chart does, or this little table here shows you, is precision and recall. If you had assigned class 0 as positive, and here's the precision recall, if we had assigned class 1 as positive. Now the support, you remember what does the support mean? Support just means how many observations were in class 0 and how many observations were in class 1. That's what support tells you. Now regarding the F1 score, you might be wondering, what is this F1 score? Well, let's consider a situation where maybe we don't really have a preference over whether we should go for a model that has a higher precision or a higher recall. Instead, we care about them just as equally. So let's go ahead and use some other metric that combines a bit of an average, some type of average of precision and recall. And that's the F1 score. That's what the F1 score represents. It's a harmonic mean between precision and recall. The reason why we're using a harmonic mean as opposed to arithmetic mean is that, let's go ahead and show you the equation there. So we can devise an F1 score. So it's precision times recall over precision plus recall. Times 2. So this is what the F1 score looks like, how you calculate it. And the reason why we use the harmonic mean is if one of those metrics are 0, then our F1 score is 0. So it's making sure that we don't sacrifice one metric all the way down to 0.